Okay, so hello, welcome back to another one of my video log recording sessions where I talk about genetic algorithms. Yeah, so the date is 2025 April 9th, and well, this video will likely be the last one of the general genetic algorithm grid search normal and hence the suffix final. And what I mean by last is this will be the last series where I sample the utility values and the constraint values from one and same distribution. So it took about how many times? Well, maybe 4 times to get this right, but yeah, I mean, I thought about not doing this video, but then again, that kind of beats the purpose of leaving video logs if I leave something like this out, so I thought doing this would give us give me closure when it comes to this part of the journey. So so again, 7 notebooks, 1, 2, 2, 3, 4, 5, 6, 7, and each from normal, log normal, uniform, exponential, von Mises, Pareto, and Weibull. So hopefully this video doesn't have to be 40 minutes long, because I think I need to do 1 or 2 more after this to talk about other things. Yeah, so we'll get to that. In these 7 notebooks, usually titled General Genetic Algorithm Grid Search Normal Final, Log Normal Final, Uniform Final, Exponential Final, von Mises Final, Pareto Final, and Weibull Final. What I've done here is everything's the same, almost the same, and this is just a nicer format. So what I've done here is per notebook, and yeah, so first I set the length of the genome, for example, genome length. It could be 10, it's 10, 40, and 100, so 3 numbers for that. And per number, I generate 10 items, for example, and 10 utility values and 10 constraint values from one of the 7 distributions, but sampled separately, so they're not exactly the same. It could be these 10 values and then somewhere like 10 values, something like that. And then I evolve, I do the evolution 5 times. Let's see if I got that right. So, oh yeah, and all of this will be done per max constraint percentage, which is used to calculate the maximum constraint by multiplying max constraint percentage by the total constraint. Total constraint. It's really hard to write this. Which max constraint is maximum constraint percentage times the total constraint. Total constraint being the sum of all these values, constraint value number 1, 1, 2, plus 2, plus 3, plus 2, all the way to constraint value n, which would and the maximum constraint will be used by the selector function to strike out entities that are over the threshold. And there are 20 percentages starting from 0.05 or 5%, 0.10, 0.15, so increasing by 0.05 all the way to 1.0. So 20 values for that. So 20 max constraint values times what was it? 5, as in 5 iterations of evolution, times 3 numbers for the genome length. And the entire thing would usually take around 105 to 110 minutes. I really need to buy a more professional gear for this. Anyway, so that's what happens. And we'll just look at the first we'll look at the normal distribution, where the utility values and constraint values are both sampled separately from a normal distribution, from the same normal distribution, but sampled differently. And not differently, sampled separately. And first, this is the peak plateau plot for 10 items, or genome length is 10, when genome length is 10. Yep. And this is the PPP for 40 items, and this is the PPP for 100 items. Awesome. And here for 10 items, back to 10 items, this is what the average dip plot looks like. So it's very usual, nothing unlike anything we've actually seen. And here are the generation to summed utility plots, or just summed utility plots, you know, along the generations or whatever. I named it. What did I name it? No, I'll just come back to that later. And then and these are for the heads. But at this moment there's actually not much use looking at these, because the peak plateau plot basically sums everything. So let's just stick to the peak plateau plot for the sake of making this video shorter, mainly to the peak plateau plot. For 40 items, the average dip plot looks like this, the average dip percentage plot looks like this, and if we go back to the peak plateau plot for 40 items, this is what it looks like. Well, at least here we see that with 40 items, the plateau, average plateau level kind of rises, and however the peak decreases, because again, as the maximum constraint percentage goes up and the maximum constraint goes up, not many entities are struck out, and therefore with the way the evolution is happening right now, not many entities or no entities are being struck out, and therefore no new entities are being created via procreation amongst the top entities, top 10 entities, for example, or with even when we use the favoring highs procreate function. And so if you look at the peak plateau plot for 100 items, this is what it looks like. Average dip plot, something very similar. Average dip percentage plot, again very similar. Very similar fashion too here. However, the average peak just dies out after, what is this? It dies after 0.7 or 70%. So this is normal distribution. Log normal distribution for 10 items. Let's go to the peak plateau plot. This is what it looks like. So this kind of looks unusual in a way, but it could be said that it's quite similar to what we have seen multiple times. Hold on, let me just bring up one of the older versions. This is log normal. So this notebook is, I wonder if I have the peak plateau plot here. Oh no, this is when things were sampled per iteration, so of course this looks different. So that's that, but I wanted to show this when this happens with log normal. It's a bit different. So going to 40 items, this is what it looks like. Going to 100 items, this is what it looks like. So regardless of the distribution, as far as these two notebooks are concerned, it seems that 40 items and 100 items don't seem to be that much different from one another, because again, this is normal distribution but 100 items. This is normal distribution but for 40 items. So these two are very similar. And same for log normal, 100 items, 40 items. So they're almost the same. So uniform distribution, peak plateau plot for 10 items, this is what it looks like. For 40 items, this is what it looks like. You see this, there's a, if you see here, the dip percentage plot just keeps going up, and even when we look at it, look at the average dip percentage plot for 40 items, it comes back down, which we can see here. They converge right here. However, the overall shape is quite similar, except towards the end where they diverge, and the average dip percentage just keeps getting wider. So 40 items for when the distribution used is uniform distribution, and 100 items. So again, these two, when it's 40 items and 100 items, look quite similar. There are some, like the curvature is a bit, big, or rather bigger here, but overall they're quite similar, or let's just say somewhat similar, I think. And exponential distribution, peak plateau plot for 10 items, just keep this in mind. 40 items, okay, kind of all the place. No, this is exponential too. Normal, log normal, uniform, Why do I have this? This is my bad. See, I knew this was wrong, because if the peak plateau plot keeps jumping about all this, all about, this is not usually right. So exponential for Mises Pareto variable, all final. 1, 2, 3, 4, 5, 6, 7. So exponential, when we have 10 items, this is what the peak plateau plot looks like. So quite similar to the previous one when we had the uniform distribution diverging towards the end. Diverging towards the end and diverging towards the end. However, 40 items. When we have 40 items using the exponential distribution, this is what happens. Yeah, so the average dip percentage, or the average dip, gets bigger towards, again, or rather around when max constraint percentage is around 0.7 or 70% until 80%, and 100 items. So this is also about the same. But one thing to note here is that when we use the exponential distribution, the average plateau level dips, again for the same reason. It's because we're actually not getting a lot of innovation through procreation, because less and less procreation is happening as the max constraint percentage goes up. I don't know if that's a good thing or a bad thing. For now, I don't like that notion. I don't like that sentiment or notion, but I can talk about that later. Von Mises distribution. Yeah, for 10 items, this is what the peak plateau plot looks like. For 40 items, this is what it looks like. So quite similar to what we have had here. We always have that steep rise and then we fall. Steep rise and then we fall. And 100 items, a steeper rise and a steeper fall. And the average plateau, it just keeps getting lower and lower. Average plateau level. So this is von Mises distribution. Pareto distribution, when we have 10 items, I bet you it diverges towards the end. Yes, it did. 40 items. So when we use the Pareto, at least with the way with how the parameters are, or how the parameters are given to the when generating the distribution, this specific distribution, it looks quite similar to when we've had, where is it, 10, 10, 10, 10 no. Okay, so for Mises, this is when we have 10 items, but somewhat surprised to see that even here, here the plateau level goes down towards the end, which is quite interesting. 40 items. Yeah, this is something something that we're very familiar with. And 100 items, even steeper. For Mises, yeah. Pareto, 10 items. Yep, something that we've seen. 40 items. Yeah, this is interesting. and 100 items. So this is quite interesting. The Pareto distribution seems to be quite similar to the normal distribution. I mean, they're not, but as far as the parameters are concerned here, parameters given are concerned here in this notebook, they are quite the same. Let me just check if I did everything correctly. Yeah, I'm using Pareto. I used Pareto, so that was okay. And variable distribution. Let me just take a sip of my beer. Ten items. 40 items. Okay. And 100 items. Okay. Yeah. Cool. Maybe, what I could do, you know, for it's been 21 minutes. So, actually, I think what I can do is, because I've never done this, and I should find a way to do this in a more elegant way. And yep. So there's 1, 2, 3, and there should be 7 of them. I'm just going to line them up. Copy and line them up. This is 40 items. This is 100 items. So, these are 10 items. Oh my god. God damn. 10 items, 40 items, and 100 items. And this is normal. I should write that later. And 10 items. So I should have 21 of these plots. This looks much better for me to actually do any kind of analysis. I should have done this way way long ago. My bad. Oh, this is how I learn, isn't it? At least now I know. I mean, I do have to do the same thing when I come up with a new way of accounting for the higher max constraint percentage values, so that even when no or only a few entities are being struck out, there's always some kind of or some level of innovation through procreation, right? This is normal. Yeah, that was fun. Really? Long normal. Uh-huh. Seriously? Yeah, this is not going to work. Uniform. What's the exponential, exponent. Mises. I think that's how you spell it. And then Pareto, and then Fable. Yep. So let's have a look. Are these two different? Yeah, they are. So this is what happens. Maybe I could. Can I? God damn it. So 10%. Oh no, 10 items. This is what happens. At 40 items, this is what happens. So this bit is unusual. Well, this bit is quite unusual. And also this. And at 100 items, this is what happens. Yeah. So, let me just save this as, I don't know what was. Actually, I could have done that later. So, sorry for going silent there for a while. I was just thinking. Yeah. Is there a way to zoom this in by 40%? No, there isn't. Maybe I could just do this. Yeah, looks better. Or not. So next up is what I'll do from now is, well, I am actually doing it, but I don't know if it's going to come through, you know, in one go. I'm running everything by mixing these distributions, and I have one more distribution that is left skewed, but I can talk about that later in another video. And hopefully when all of that is done, I can have all the pictures, because right now I only have 21 plots, 21 peak plateau plots. Then I can have multiple. I'll probably have 64 plots. Yeah, I'll talk about that later. Yeah, I think that's about it. So thanks for watching. I'll see you later. Bye.